Hi, welcome back to our weekly lecture focusing on serverless technologies. So now that you know a little bit about the sort of use cases around Lambda functions, how do these Lambda functions actually work? Well, let's take a look at the steps involved in working with and building Lambda functions. First of all, when you're working with a Lambda function, you have to write the actual application code. You have to write the Lambda function. Next, you create a Lambda function resource in AWS. You basically have to create so you've written the application code, and now you have to create a resource which includes both the application code and the configuration of the Lambda function itself. Then you deploy the Lambda function into an AWS environment. You run the Lambda function, and you run the function by triggering it with some sort of event. And then finally, you will want to be able to monitor that function so you can understand what is going on when that function is invoked. Is it producing error, generating error messages? How much time is it taking to invoke the function, and so on. So let's look at each of these steps in more detail. The first step involved working with Lambda functions is actually writing the Lambda function code. And when you write the Lambda function code, you can select from a number of different programming languages. Lambda functions support Node.JS code, which is JavaScript, Java code, Python, C Sharp, and Go. And I know that AWS is adding new programming languages over time. So you start by writing your Lambda function in one of these programming languages. And oftentimes you'll need to add in some sort of, set of external code libraries that you're calling within your function. Those have to be packaged into the function. The exception is the AWS SDK. The actual AWS SDK library is always packaged within your Lambda function environment. So you don't necessarily have to specifically include the SDK in your function, although there might be good reasons for doing so, which I'll talk about later. But one thing that keep in mind is that when you're designing your Lambda function, you have to remember that Lambda functions are completely stateless, meaning that every single time the Lambda function is invoked, there is no state information stored within that Lambda function. So the Lambda function is not able to access any information from previous requests or previous invocations of that function. Any sort of state needs to be persisted in some sort of database outside of the Lambda function. So when you think about it from an application perspective, every single time that Lambda function is being invoked, it's like it's being invoked in a brand new, fresh, clean environment with no state information. And also, Lambda functions are ephemeral, meaning that Lambda functions will disappear on you. So Lambda functions only live for a very short period of time. So they're truly ephemeral. Now, think of it like, like every time you invoke the Lambda function, you're potentially working with a brand new environment. So Lambda functions are both stateless and ephemeral. So once you write the Lambda function, then you need to create a Lambda function resource. And there are a couple different ways to do that. You can create the Lambda function resource using the AWS Lambda Web Console, and I'll show you a demonstration of how to do that in a bit. You can also use CloudFormation to create Lambda function resources, And of course, you can always use the AWS API directly to create these resources. When you create a Lambda function resource, what you are doing is you're specifying a number of things. First of all, you're specifying the application code that's going to run in that Lambda function resource. You're going to specify the region where that function is going to run in, and you're going to specify a certain amount of memory that you're going to allocate to that function. You don't get to allocate CPU directly, but you do get to allocate memory. And the lowest amount of memory you can allocate to a function is 128 megs. And this goes all the way up, at least at the time of this video recording, up to around 3 gigabytes of memory. And you can adjust the memory allocation in 64 megabyte increments. One thing that's interesting is that the more memory that you allocate to a Lambda function, the more CPU is also going to be allocated proportionally and automatically by AWS. So you have this Lambda function, you define the region it's going to run in, you've allocated a certain amount of memory. You also need to specify an execution role that the function will use to access other AWS resources. When a Lambda function executes, it has to have some sort of permissions, oftentimes, to communicate with other resources. For example, you might create a Lambda function that is able to write and read data from something like a DynamoDB database table. Well, that Lambda function needs to have an execution role with a policy permission allowing access to that particular database table or that DynamoDB service. Without that permission and without that execution role, the Lambda function would not be able to access these external services. And so that's an important thing to keep in mind. Every time you create a Lambda function, you have to create a corresponding execution role for that function, which specifies all the other services that Lambda function needs to be able to connect to. And then finally, with the Lambda function, you define a concurrency level, which means that you can specify the number of simultaneous Lambda function executions that are allowed in your environment. Well, what does that mean? Well, remember, every single time a Lambda function runs, it is being triggered by some sort of event. And every single event runs only in one single Lambda function. That means that if you have a Lambda function that's being triggered by a web request, every single web request is going to run in a separate Lambda function, a separate invocation of a Lambda function. And your platform might receive 100 web requests simultaneously. Each web request is going to trigger a Lambda function and run in a separate Lambda function. So you could have 100 Lambda functions running simultaneously. Well, you might want to be able to control the number of concurrent Lambda functions that are running simultaneously. And so you can control that on a per Lambda function or per resource level by setting this concurrency level. Okay, so you've written your Lambda function code. You've created a Lambda resource, and now you're going to deploy your code. Deploying your code is there's a number of different ways you can do it. You can author your code directly in the AWS Lambda console. There's an actual like a text editor, a code editor, a web-based code editor that you can use in the Lambda console to create your code and deploy it into that Lambda resource. You can also package your code on your own laptop or workstation. You could package your code and libraries into a zip file, and then upload it into an S3 bucket, and then point that Lambda function at the package in the S3 bucket. So the Lambda resource now is pointing at this packaged Lambda function code that is living in an S3 bucket somewhere. You can create your Lambda function code and put it directly into a CloudFormation template, or use one of the serverless frameworks that I'll show you later in the lecture. And you can also publish code directly from some sort of integrated development environment. Like Microsoft Visual Studio has a plugin which allows you to directly edit and publish Lambda code. AWS also has a web-based code editing environment called Cloud9 that can also directly publish code into Lambda resources. So there's a variety of ways to get your Lambda function code published up into AWS and connected to your Lambda resource. So once your code is published and you have an existing Lambda resource, now you can run that Lambda function. And you run that Lambda function by triggering it using some sort of an event. And there are a wide variety of different event-driven triggers that are available from different AWS resources. When you set up these event triggers to invoke the execution of a Lambda function, we call that setting up an event source mapping. And you can use services like S3 or DynamoDB, Kinesis, CloudWatch, and several other services to configure event triggers for Lambda functions. You can set up different AWS endpoints, and if these endpoints receive a request, that can also trigger a Lambda function. For example, you can set up an AWS API gateway, which we'll talk about later in the lecture. And if the gateway receives a web request, then it can trigger a Lambda function and pass that web request onto the Lambda function for execution. Similar with the Internet of Things service in AWS, you can set up an MQTT gateway that also will receive requests and then trigger Lambda functions. And finally, you can run your code based on a scheduled trigger. In the CloudWatch service, you can set up scheduled tasks that are sort of like cron jobs in a traditional Unix or Linux environment. And these scheduled tasks can automatically trigger the execution of a Lambda function. That's really helpful for automating different processes that need to be triggered on, like, an hourly or daily basis. Oftentimes I'll use a scheduled trigger if I need to initiate some sort of like cleanup or sort of pruning job in an environment. And I'll write that job in a Lambda function and have it triggered by a scheduled CloudWatch task. So when after we invoke our functions and they run, they do their thing, and then they terminate, over time we'll be invoking our functions thousands, maybe millions of times. We want to have a way to be able to monitor what is going on with our Lambda functions. And you can do that using the CloudWatch service. The Lambda functions will automatically push code metrics into CloudWatch, and you can view all kinds of graphs and logs to understand what's going on. So CloudWatch will show you things like how many requests the Lambda function is handling. It'll show you the error rate. It'll show you the latency, how long it takes for a Lambda function, a typical average Lambda function to run and execute the code. It'll also show you if a Lambda function's being throttled, which, if the demand for a Lambda function is too high, if it exceeds the concurrency level set for that function, then subsequent Lambda function invocations might be throttled. In other words, AWS simply will not run the Lambda function if there's too many concurrent requests already occurring. So it can be important to keep an eye on that throttling code metric because that could really impair the performance of your platform. These Lambda functions will generally create some sort of execution log, and you can look at the execution log for a function for troubleshooting information or for performance information. These execution logs are stored in CloudWatch logs, and so you can look at application logs and see maybe stack trace information if there are exceptions being generated by your Lambda function. And finally, another way to monitor your Lambda function is to use a service called AWS X-Ray. What AWS X-Ray does is it provides distributed application tracing. And what that means is that AWS X-Ray can show you how your Lambda function is interacting with other AWS services. And most importantly, it shows you the latency involved in those interactions. So if your Lambda function is communicating with like a bunch of different database tables, you might want to understand, well, what is the performance of these interactions and how is that latency impacting the overall performance or latency of the Lambda function itself? So this is great for troubleshooting performance problems with Lambda functions. Here's a quick example of a very simple X-ray trace showing that an event has triggered a Lambda function. This Lambda function triggered another Lambda function, which then communicated with a DynamoDB table and the Amazon recognition service. And it shows you the amount of time that is spent in each one of these particular tasks. So it allows you to sort of get a deep dive, introspective understanding of what is going on when your function is being invoked and your function is communicating with other services. So now that you know a little bit about how to work with Lambda functions, and you write the Lambda function, create the Lambda resource, and then you would deploy your code into the Lambda function and run it and then monitor it. You might be asking yourself the question, well, how does all this work? How does this magic happen behind the scenes? How is AWS actually running my Lambda function? And how is AWS running my code? Well, there's no real magic happening behind the scenes. What's actually happening is that when an event triggers a Lambda function, what AWS is doing is it's creating a Lambda execution environment using a container. So we've already talked about containers in this course, and this is a key area where containers are being leveraged. Every time a Lambda function is triggered, a container is created, and a container will run. And when a container is created, we call that a cold start. When the container is created by AWS, the Lambda service is going to deploy your Lambda function code into that container environment. And it's going to provide any sort of bootstrapping that is necessary to execute your Lambda function code. For example, if you had written your Lambda function in Java code, then the container would need to start up a Java virtual machine environment in order to run your Java code. So once that container environment is up and running, then your code is going to execute like any other normal application that might be running in a container or on an EC2 instance or on your laptop. It's just simply going to be running in this containerized environment. What's interesting about Lambda is that each each Lambda function invocation runs in a separate container. So it's never the case that a single container is supporting multiple requests simultaneously. What that means is that you don't have to worry about any sort of blocking operations within the container environment, because every single request, every single invocation is going to go and get routed to a completely separate Lambda function running in a separate container. Now, these containers, the Lambda function can only run for a certain amount of time. Lambda functions can't run, at least currently, at the time of this video, they can't run for longer than 5 minutes. And after the Lambda function finishes its execution, then the Lambda function terminates. The Lambda function goes away. But what's interesting is that the underlying container that was running that Lambda function, that container may persist for some period of time. And if you invoke the Lambda function again, it's possible that the Lambda function might trigger an execution in the same environment as a previous Lambda function. Now, I'm not trying to confuse you here. Remember earlier I said that you have to treat these environments as ephemeral. The reality is that sort of behind the scenes, under the hood, there is a container, and those containers are not necessarily they're not necessarily terminated immediately after the Lambda function finishes running. AWS may keep those containers around for a little while, just in case you decide to trigger that Lambda function again, because then there's less effort required to create the container and build up and bootstrap the container environment. It's sort of like, you can think of it as sort of like AWS is caching the Lambda function environment in the background for a certain period of time. And we don't really know how long it might cache it for. It could cache it for 5 minutes. It could cache it for 20 minutes. We could cache it for hours. But the way you build your application, you should always assume that your code is going to be running in a fresh, brand new environment, that it's truly ephemeral. So if your Lambda function is triggered and that Lambda function is executed in an existing container environment, then the Lambda function will actually run faster because it doesn't have to go through the Lambda environment creation and bootstrapping phase. And we call this a warm start. So a Lambda function which starts from a fresh, brand new, clean environment from scratch goes through a cold start cycle. The Lambda function, which is going to be invoked and run in an existing container environment, represents a warm start environment. One other thing I'll mention is that these container environments that are set up to run our Lambda functions actually do have a small amount of storage available within the container itself. There's a temp directory with about 500 megabytes of storage space that you can kind of use as a scratch space if you're doing some sort of, like data manipulation operations or something. But you should never count on this space being persistent. You don't ever want to store actual and write data into the file system in a container with the expectation that that data is going to persist and be available for subsequent invocations of the Lambda function. That's simply not going to be the case. And you should always treat the Lambda function environment as being an ephemeral environment. Well, so how does AWS price out this Lambda uh, function service? And what are the costs associated with Lambda? Well, there's a sort of a free tier or band of service that's available each month. The first 1 million requests for a Lambda function are free each month, and then you pay 20 cents per million requests thereafter. And a million requests, you might be thinking, "Oh my gosh, I can't believe it. That's a lot." Well, it depends. You could have an application that's getting hundreds of millions of requests a month easily if you have lots of customers. But if it's a very simple Lambda function, if it's like a utility function, it's just invoked, once an hour or something, then there's really not going to be any cost to invoking that Lambda function because you might only invoke it, something like, tens of thousands of times a month versus a millions of times a month. So you pay for the number of requests that are made. You also pay for the amount of time that is spent executing your Lambda function. And AWS gives you the first 400,000 gigabyte seconds of compute time per month free. And so it's not just the amount of time that is spent uh, in running that Lambda function. It's also how much memory you've allocated to the Lambda function. So there is a sort of a formula that's based on the execution time, multiplied by the memory allocation. And there you can find tables out there that help you understand, like, if you allocate 1 gigabyte versus 2 gigabytes, how much is it going to cost you based upon an average execution time of, 500 milliseconds or something. And then the other thing to note is that oftentimes you'll use a Lambda function to connect to other services. And of course, you're going to pay for those other services. So if you have a Lambda function that's generating data and then storing that data into S3, you are going to pay for the data that's being stored in S3. And so that should be pretty obvious to you by now. I want to say a couple things about Lambda function performance in particular. Now that you have a little bit better understanding of what's going on behind the scenes, remember, AWS is actually using containers in the background to run and support these Lambda functions. Every invocation of a Lambda function is going to run in a separate container, and sometimes AWS has to create new containers, which are called cold starts. And sometimes AWS can invoke a Lambda function in an already existing container, which is called a warm start. And this cold versus warm start issue is really important to understand because it can dramatically impact the performance of Lambda functions and of your serverless platform. I mentioned earlier that once a Lambda function container has been created, that container, that execution environment may exist and may persist for some amount of time, even after the Lambda function is done running. There's no guarantee, however, how long that container is going to persist. It's going to persist for as long as AWS allows it to persist, which is never going to be more than a few hours. But it could be just a few minutes. It totally depends on their backend algorithms and I suppose how much demand there is for their Lambda service. What we know from practice is that the more frequent you invoke or exercise a Lambda function, the more performant that Lambda function is going to be. That's simply because Lambda functions which are invoked frequently are being kept warm in the Lambda environment. These functions, their execution environments have been created, and because they're being triggered so often, the Lambda function environment is just naturally kept warm. Versus a function which is only triggered maybe once an hour or a few times a day. Oftentimes, those Lambda function invocations are going to trigger a cold start, meaning the AWS has to create a brand new execution environment for the container. The cold start time, the time that it takes to create the container execution environment and bootstrap that environment can vary greatly depending on the nature of the function. So if you create a function and write it in Java, that cold start time is going to be significantly slower than Python. And the reason is because in a Java environment, you have to bootstrap the creation of the Java virtual machine. In Python, because it's an interpreted language, you don't need to do that. And so the Lambda function can begin executing much faster in a Python environment versus a Java environment. That doesn't mean the Python code runs faster. It just means that there's less upfront bootstrapping time required to actually invoke the function. If the if the Lambda function is connecting to other AWS resources, like say DynamoDB, then there's a certain amount of time that's required to set up that connection to the database service. So that can impact the cold start time for a Lambda function. And then finally, if a Lambda function needs to communicate with resources within a VPC, then that can significantly increase the amount of time that's required for the cold start because a VPC connection requires an IP address. So the Lambda actually has an IP address within the VPC in order to connect with other private resources within that VPC. Example of how the warm start time and cold start time can vary greatly. So this is based on some statistics that an organization created. So there was an organization, they did a bunch of testing and they published these statistics showing the difference between cold starts and warm starts. And you can see that these warm starts, whether they're networked or not, these warm starts only take about 32 to 56 milliseconds, very short period of time, versus a cold start could take anywhere from 200 milliseconds to almost a full second. And in the case where you're connecting to a VPC-based resource, a cold start can take up to 10 seconds. So the performance of your Lambda function can vary greatly depending on whether it's being invoked as part of a cold start or a warm start. So there are a couple other things to keep in mind when it comes to Lambda function performance, and these are based on real world findings that companies have shared, at conferences and so on. One thing to keep in mind is that, yes, cold starts can be a significant issue with your Lambda function performance, but there are cases where cold start performance is actually trivial compared to the time it takes for a Lambda function to establish a connection with some sort of external resource, like a database or something like an API gateway. If the Lambda function has to negotiate a TLS connection with some sort of external resource, that that external connection um, establishment could take longer than the actual cold start time of the Lambda function. So you have to keep things in perspective in that sense. Um, if you allocate more memory to a Lambda function, then what AWS will do is it will allocate more CPU to the Lambda function. And what we found is that when you allocate more than 1.8 gigabytes of memory to a Lambda function, then the Lambda function will run on 2 CPU cores instead of one, which means that the Lambda function in some cases, depending upon the nature of the function, might actually execute faster when you give it more memory. That's not always the case, however, and you have to test to make sure that that makes a difference. Because also remember that the more memory you allocate to the function, the more it's expensive the function is going to be, the more it's going to cost. Sometimes we've found in practice that cold functions actually start faster than warm. So this is sort of an anomaly that occurs from time to time. Um, and when you have millions of invocations, there might be cases where cold functions will start faster than warm functions. When you're creating these functions, one of the things to think about is, how much should what should the function be doing, and how much functionality should you be packing into that Lambda function? There are sometimes some cases where companies will build these sort of large monolithic functions that encapsulate quite a bit of functionality. Oftentimes we'll see better performance if the Lambda function is designed to do less. In other words, if the Lambda function has a narrower, more specific purpose, the Lambda function is smaller and can oftentimes be more performant. But again, this is something that you have to test out. It's not always the case that big functions run slower and small functions run faster. You have to experiment and test your Lambda functions to see what's going to give you the best results.